Hello all, welcome to today's lecture. This is the first lecture for the Lasers and its Application course PH5814. To begin with, basically we all are familiar with lasers and we know that there are certain cases where we need to use a laser rather than any other light sources. So that brings us to the very specific properties of a laser beam. So if we talk of properties, we all know that there are certain specific terms that come in. First and foremost, I would say, let's say intensity. So there are various applications in which the intensity of the laser, which is considerably high compared to any other sources like LEDs and any other broadband sources, lamps and so on. So here these sort of applications, for example, micro machining, laser LASIK and so on. LASIK need not have very intense but a very focused collimated beam. So let's get into this, can go into the next point. So intensity is needed, and in such cases we use lasers where we use light to cut metals and so on. Even semiconductors like silicon substrates and so on can be etched out using a laser beam. The next property is of course collimation. The collimation means the beams can be very nicely collimated and focused down into a very small spot, and that is practically where the use of laser happens, like in eye surgery, in LASIK and so on, where you need a very tight spot and a very controlled intensity and to guide the light as you do the surgery. So collimation. And all this collimation typically is ceded to the fact that the laser beam is actually a quasi-monochromatic light. So I am not writing monochromatic but a quasi-chromatic. I am writing quasi-monochromatic because nothing is monochromatic. It's not a single wavelength. It always will have a line width, which we will discuss in much details in the later lectures. But still it's a very narrow beam, especially for a continuous wave laser. The line width is very small, which gives it like a very pure color, and that helps in the collimation and focusing of the beam in a very precise spot. And this the fact that it is very monochromatic, it's a very less line width, leads to the fact that the laser beam is a very coherent source. So there is coherence. So the first thing that comes to mind when I ask in class as to what is the property of a laser beam, we hear coherence. So this is the topic of today's lecture, that what is coherence and what are we going to, how do we define it. So to start off, first and foremost, I can say that nothing is totally coherent and nothing is totally incoherent. There is a degree of coherence for every sources. So of course an LED light also will have a certain degree of coherence, the coherence length being very, very short, while for a laser beam the coherence length is very, very long, so it has a higher coherence. But still a laser will also lose a coherence if you go beyond a certain length or distance or time. And so how do we quantify these values or compare two different sources as to which one is more coherent or not? There are two ways of defining coherence. One is called the temporal coherence, which is basically, as the name suggests, it's in time. So as the wave propagates, how long it takes for it to become incoherent. And the other one is the spatial coherence. So for example, if you consider a spot or a broad source of light, and you consider the beam as it propagates across the cross section of the beam, how long the coherence sustains. So that is called the spatial coherence. So today's lecture we will be talking about a little quantification of these two parameters. So temporal coherence. To come to this whole part, let's just look into the interference. Because as we said, so how do we define Coherence, now it's like if a beam is coherent, it gives rise to interference pattern. So let's have a look as to what we understand. So when I ask what is coherence, the normal answer that comes out is the beams are in phase with one another, or they all have the same phase. That's what the answer comes, but that's not really the right thing to say. So for coherence, what we understand is that there is a constant phase relation. It need not constant phase relation between the different parts of the beam. So it's not that the phase is same for all. They can have different phases, but the phase should not change with time. So it has to be a constant. So let's have a look into this, how it arises. So typically, when we consider interference, it's basically sum of two electric fields associated to the electromagnetic wave. So the electric field, let's say we interfere two waves. So the first wave, the electric field is given by E1. It is written as E01, which is the amplitude of the wave, and the phase term, which is exponential minus I kz minus omega t. It's a very simplified form where the beam is propagating along the z direction, and the k is the wave vector, omega is the angular frequency, this is the amplitude. They're all in it's a polarized beam, and I have removed the vector signs. It's only the amplitude I'm talking of, a magnitude I'm talking of. And the other beam is given by E2, so it's only the magnitude, please remember. So you can put in the unit vectors to define the direction as well. So this comes out to be, so this has to be k1 and omega 1, and this has to be k2z. It's another beam with a different frequency, right? And these two are meant to interfere. Interfere means superposition, and superposition means addition of the electric field. Okay, so let's not write this. Superposition means addition of the field. So we have a net electric field E total, which is nothing but E01, E1 plus E2. Now when we measure, what we do in an experiment, what we measure is not the electric field, we rather measure the intensity, which is I, and it's given by mod E total square, which is E1 plus E2 square, right? And once we are done with this portion, I am actually not doing the maths because you can just solve it. So you plug in the values, these two values of electric fields in this, and there's an exponential term. If you look into it, what you will eventually get is E01 square plus E02 square plus twice E1, twice E01 E02 cos theta, where theta is nothing but the phase difference. So we had k1 minus k2 z plus omega 1 minus omega 2 z. So if you just plug the values of these two values of E1 and E2 in this equation and find the square of that, this is what you come to have. So this is the equation I am interested in. So you see that this phase I'm talking of, so long we are talking of phases, phase is nothing but this one, the relative phase of the two waves. So if theta is fluctuating, it is changing with time, then as you average cos theta with time, cos theta averaged over a whole cycle becomes 0. So for incoherence, the way we call it, that theta changes, there is no constant phase relation. So practically you are averaging over the whole cycle. All values of theta can happen. from -1 to +1, or cos theta can happen from -1 to +1. If you do that, this this term becomes 0, and so in that case your intensity, maybe I'll use another color. So the intensity for incoherence becomes nothing but E01 square plus E02 square. Okay, so what does it mean? This is nothing but the intensity of the first beam plus the intensity of the second beam. This is exactly what we see in a normal case when you shine a torch. So the net intensity is just the sum of the two individual intensities that are shining. There is no pattern, nothing. So what is the second case is the coherent case. So in the coherent case, all we said is that theta is constant. I mean, the relation is constant. Now depending on your, so you see here theta has a z and a t. Sorry, this is t, right? This is t, z and t. So when at different times, different z's, there is a certain value of theta that we can say. So if you look into a space, at every point there is a certain value of phase. So in that case, your cos theta actually varies from -1 to +1, but each definite point has a definite phase. If that is the case, then what happens? It's easy to see from here. So let's say if E01 was equal to E02, so that is the one ideal case where both the beams have same intensity. If that is the case, then the net intensity becomes twice E01. I mean, I'm just replacing all the E02s in this relation with E01s, and if that is the thing, then you have this plus 2 square E01 square cos theta. So if you see this, when theta is 0, so cos 0 is 1, then your I intensity becomes 4 times E01 square, right? So ideally it was twice E01 square, that is just the sum of the two amplitudes, two intensities of the individual beam. Now the intensity is actually twice of that. So it is 4 E01 square. And the other scenario is that other extreme is so here your cos theta is 1, and when theta is pi, which is basically out of phase condition, your cos theta is -1. In that case, your I becomes 0. So I have a minimas are defined by this minima, and maxima are defined by this relation. So you do have an interference pattern. Okay, so if that is, so this is where we see that we needed to have a coherent case where we had theta to be constant. Of course, it's a at a given time is constant, so it's at a given spot is constant. So some place it will be a maxima and some place it will be a minima. Well and good. So knowing this, let's go ahead with the temporal coherence that we already talked about. So temporal coherence, what do I do here? So let's consider a situation where I have two waves again. So I have one wave which is going at a certain has a certain frequency, and the other wave has a slightly different frequency. Let's say it has a slightly longer wavelength, so slightly smaller frequency. So if you see it, as it goes further, so they start off at the same point, at same phase, so both of them are 0 here, and then as the wave propagates, the separation between the waves increase, right? And so there will be a certain after a certain distance they will become out of phase. That certain distance is actually called the coherence length. Coherence length is basically given by LC, which is the point or the distance at which the beams become totally out of phase. Okay, if that is the situation, then LC, and as you see here that this LC should be proportional, or rather inversely proportional to 1 by delta nu. If this this one had a nu 2 frequency, so the coherence length will be inversely proportional to the difference in the frequency. So if this was nu 2, this would be nu 1, then the difference, as you see, if the difference in frequency is large, then this the point at which they become totally incoherent, I mean totally out of phase, will be very short. If they are very similar in frequency, they can go a long distance until they become out of phase. So of course it is inversely proportional to the delta nu, the difference in frequency of the two beams. And because it's a length, so of course LC is nothing but C by delta nu. Now all we have to do is convert it into lambda in case you want to present it as lambda. So consider what am I talking of? Let's say this is the spectrum, So this can be either increasing nu or the lambda goes up in this direction. So this width is either delta lambda in terms of delta lambda, or in terms of delta nu is what you can represent. So what is the width of the frequency range that is there in the beam? Now LC is C by delta nu, and then we all know that nu is C by lambda, and therefore delta nu is minus C by lambda square delta lambda. And substituting this thing in the expression for LC, we have LC is nothing but lambda square by delta lambda, ignoring the negative sign which is not needed here. So this is called the coherence length. And this has to do with, I am not shifting in space or anything, it is in time. So how far the beam can travel before it becomes incoherent, and that is proportional to the lambda square and also inversely proportional to delta lambda. This is what you have to remember. So the other sort of coherence that I said was the spatial coherence. This is more a little qualitative form that I'll be discussing here. So consider a source of light with, so you can consider two spots on the source which is separated by a distance s. And now I have, so this is the distance, and I have another observation point where I am sitting A, and so these two beams are, the beams from these two spots are traveling to A. This A is at a distance r from the S. Now this by spatial coherence I mean that consider another point, let's say it is at a distance L t, because we call it LT because spatial coherence is also called transverse coherence, because we are in the same plane of observation, we are just laterally going in the transverse direction, we are going away and seeing how far we can go from this spot till we see the beam is still coherent. So the spot size rather is what we are talking of. So how far we can go away from A, so how far, let's say this is B, so where the coherence is now lost. Okay, so in this scenario, the way one can define, first you can think of it that LT should be proportional. So the LT can be large if R is large. So R has to, larger R means what? The separation of the two source points are nearly negligible, so you can't make out their separation. So LT is large when R is large, and LT is inversely proportional to S. So if S gets bigger, of course your coherence, lateral transverse coherence length becomes smaller. With this in mind, and of course there will be a lambda factor, we come down to LT is equal to R lambda by S, and this is nothing but, it can be somewhat written as lambda by theta S, where theta is taken to be this angle between here, this is called theta S. So for small theta. So this is what we call as the spatial or the transverse coherence which is basically we are sitting at a certain distance from the source, and if we go in the transverse direction in the plane of this observation, how far can we go within the spot basically, so that the coherence stays, and that will depend on the size of the source. So how much is S, how much are the separations between the source points, and how far you are from the source. That is where we stop today. So please note that these two boxes you have to remember. One is the coherence, the temporal coherence length, that is basically how far the beam propagates before it loses its coherence, and the second one is the transverse coherence, which is how far you can go from the central beam. I mean, laterally you move out of the beam and still keep the coherence. So that's where we stop today. Thank you.